Before we discuss the surface circulation of the ocean, there's two more concepts that need to be introduced. The Ekman transport and the concept of geostrophic balance. Both of these have to do with the rotation of the Earth. So let's start with Ekman transport. So consider a simplified situation where we have an ocean that's made up of a bunch of thin horizontal layers, like a deck of cards. And we're going to assume that the wind pushes on the top layer or flows across the top layer, and it imparts some of its momentum, generally around 2 to 5% of its momentum, goes into that top layer of the ocean. And then there is friction between the layers. So some amount of the momentum from the movement of the top layer will be transferred to the next layer down, but it's not 100%. So there'll be energy lost as it goes down, the momentum goes down through the different layers. So as the wind blows over the top layer of the ocean, that layer will move in the northern hemisphere to the right. Theoretically, it's 45 degrees to the right of the wind in the northern hemisphere, and it would be 45 degrees to the left of the wind in the southern hemisphere. Now that top layer pushes on the layer below it, so it transfers some of its momentum to the layer below it, and that layer below is also going to be deflected to the right in the northern hemisphere, and because it's only transferring some of the momentum, its speed will be slower. And then we go down to the third layer, so it's going to move further to the right from the layer above, and as only a fraction of the energy is being transferred, its magnitude will be lower, and so on and so forth. So for the northern hemisphere, as we increase our depth, the direction of the currents moves further and further to the right, and the magnitude of the currents decreases. And this results in what's known as an Ekman spiral. So you can see here the wind in the layers going to the right and decreasing, and will eventually go in an opposite direction to the wind, but at a much lower magnitude. So it creates this spiral. And this spiral, depending on the latitude and the wind speed, can be 10 to 100 meters thick. So the depth at which the current is going in the opposite direction to the wind is known as the Ekman depth. And the layer of water above that, so within the spiral, is known as the Ekman layer. So the net transport, which comes from integrating all the different arrows throughout that Ekman layer depth, so as they spiral around to going back against the wind over that entire layer, the net transport, so the integral motion of that whole Ekman layer, is going in the northern hemisphere 90 degrees to the wind. So the net transport of this thick layer here is 90 degrees to the right of the wind, or in the northern hemisphere, and to the left in the southern hemisphere. So just a quick summary. So the Ekman spiral is the current direction throughout the Ekman layer as it spiral, as it moves further and further to the right. The Ekman transport is the net transport over that layer, which is 90 degrees to the direction of the wind, either to the right or the left, depending on which hemisphere you're in. The Ekman layer depth increases with wind speed and decreases with latitude, and hence the stronger the wind, the deeper the layer, the faster the currents are moving, the larger the net transport, the larger the Ekman transport. So the other concept that we need to look at is that of geostrophic balance. So this has to do with flow going down a pressure gradient. So here we have a wedge of water. So at this level here at the bottom, we've got more water on this side. So at this point, there's high pressure here and lower pressure under the smaller amount of water. So we know that in the absence of rotation, the flow is going to want to go from high pressure to low pressure. So the effect is that this wedge of water would like to flatten itself out. We also know that due to Coriolis, the flow comes down the pressure gradient, it's deflected to the right in the northern hemisphere, We have a Coriolis vector here at right angles to the flow, and we still have a pressure gradient force that's down slope, so from high pressure to low pressure. The flow is going to continue to accelerate, and therefore there's going to be more Coriolis effect on the flow, and it's going to continue to be deflected to the right in the northern hemisphere until we eventually get to a situation where this Coriolis vector exactly balances the pressure gradient force vector. So these two vectors are in opposite directions and have the same length. And at this point, the flow is perpendicular to the Coriolis vector, so it's now going along the slope. So it's no longer got a downslope component, it is running along the slope. So if this was a hill, it would be going around a contour of that hill. Because it's driven by Coriolis in the northern hemisphere, this flow is to the right when you're looking down the pressure gradient, and if in the southern hemisphere, it's to the left when you're looking down the pressure gradient.